Okay, so we are starting on to passive transport. We are diving a little bit deeper into the world of cellular transport. We're going to break it down over the next couple days into passive and active transport, kind of like the flow chart that you were working on. So the first thing, I'm going to do a demo. People on the video, you'll be able to watch the same video on the notes. So any of you who rewatch it, you can just watch it on the notes. But I'm going to pause it. I'm going to do a little demo here. And under analysis 1, I want you to, just like we did previously, write down what do you see, what do you think, what do you notice about this demo. In this demo, we did see that the hot water made the dye spread a little bit faster. It was kind of hard to notice with this one, so I might try it with like boiling water for next period. But in this case, we are going to be talking about something called Brownian motion. So this is a kind of simple concept. We're not going to talk a whole lot about it, but we're going to be talking about it, at least for the sake of this. Brownian motion states that all molecules, even the most solidly packed ice particles, all of those, are in constant motion. So your desks are in constant motion. All of the particles in your body are in constant motion. The gas around you is in constant motion. Not quite. So it can range from bouncing around the walls to vibrating in place. They're still moving around. So you saw in this that the particles spread out because, again, they're in constant motion. They're going to move slowly, but they're going to spread out. And that's something we're going to see for passive and active transport, is that we are going to be watching the molecules and kind of how they move through the system. So there's the video if you want to watch it again. And the first thing we need to establish before we actually talk about passive transport is something called a concentration gradient. So how many of you guys have played with gradients before? Have ever made a PowerPoint or a fancy Word doc or something like that? What is a gradient?
Flow of some
It's like smoothly transitioning from one to another through like fading between them.
Okay. So yeah, you are changing from one thing to another. Noah, did you have something to add?
It's like a color gradient.
Okay, so color gradients, yes, you can shift from one color to another. You may not be able to notice on this slide, but there is actually a gradient from white to kind of a gray color here at the bottom.
Is that blue 5?
Stop.
Blue 40.
So, in this case, a concentration gradient is going to be just like that. We are moving particles over a distance. It's going to happen gradually. So we are going from very few particles slowly over to a lot of particles. And these particles are going to move from high concentration to low concentration. So typically that's the way they want to move. Kind of like I said with all of the negatively charged molecules or all of the positively charged molecules, they want to stay as far away from each other as possible. They have to do this through movement. So this concentration gradient is going to move the molecules from high concentration to low concentration. A good way to analogize this, it's going to be weird, I will say that. Someone farts in an elevator, and there's a whole bunch of people in there. You want to get out of the elevator. You want to spread as far away from it as possible. Same thing with this. They want to be as far away as possible, so they are going to spread out to an area where there is less, in this case, fart or particles or whatever. Yes, so weird analogy, but it kind of makes sense. I will also be having you tie it back to the hallways, so you'll get to see that as well. But this concentration gradient is going to be very important for diffusion and for facilitated diffusion and all the types of passive transport, because they're all going to follow this rule. So passive transport, we said the other day, is going to be transportation of materials without the use of energy. So what was the type of energy that we talked about? ATP. So this type of transport is going to move materials, move particles without ATP. That's why it's passive. It's not using energy. It's kind of like if you were last weekend just hanging out on the couch, just not doing anything, not using energy, not being active. That would be passive. I mean, yes, you are still using energy, but not near as much as if you are running laps. So that would be passive transport. So we're not going to use energy. Need more time. Okay. So these, oh, nope, I have drawings on there. So these molecules, like I said, they are always going to be in movement. So if we had a piece of dialysis tubing or something like that, we would be able to separate the dye from the rest of the water, but as they try to spread out, they will start to cross this barrier, this membrane, and their goal is to spread out. If we have multiple solutions trying to maintain equilibrium, they're going to kind of trade places. Their goal, again, is to hit equilibrium. They want to be equal on both sides of the membrane, both sides of the wall. And this type of equilibrium is called dynamic equilibrium. So these molecules are going to be constantly moving even though they are equal or they are equally spread out. So even though they are happy where they are still in constant motion. So they're going to be spreading out. So again, if I opened up the gas valve here, not that it's turned on, the gas would start to spread out in the room, and it would equalize throughout the room.
That would be hilarious if that was actually on.
Oh, it was on earlier.
Oh.
It's not on right now. I have the gas turned off. But if I had this on, it would start producing gas, which would start to fill up the room. The gas would try to spread out until it reached an equal point where you probably couldn't smell it as well because it's spread out the whole room. It would still be in motion. It would still be bouncing off all of the walls. It would still be bouncing wherever. And if we open the door, it would start to migrate from this room where it is kind of concentrated out into the hallway where it's even less concentrated. So the goal of all molecules is to get as equal as possible. So if it could spread out, also if we open the windows, it would go out that way and try to fill up as much space out there as it can. Any questions about equilibrium? Okay. So, take some time with your partner. Using this picture, describe what's happening based on what we've just learned about equilibrium and about diffusion. Okay. So facilitated diffusion, like we said, are going to have to use proteins to get across. There are going to be two different types of proteins that we're going to talk about. The first one is the channel protein, and the second one is the carrier protein. So a channel protein is going to be more of a tube. It's going to help to open and close and help move molecules through the membrane. So it's going to have a little gate on it that'll open or close, whether things are supposed to get in or not. Carrier proteins, on the other hand, are going to change their shape to let a molecule through, or a couple molecules through. So the carrier proteins are going to physically carry the molecules across. Think channels. Where have you heard of a channel before? Not other than TV.
The English channel.
The English Channel, or maybe the Panama Canal, or what are the landmark channels supposed to be? Like what is a channel? And I'm not talking TV.
Helps move things.
So it helps move boats. It's like a pathway. It's going to allow things to move through. So the English Channel or the Panama Canal. The Panama Canal we built literally just so we could get boats from the Atlantic Ocean to the Pacific Ocean without having to go the whole way around Brazil or South America. So channel proteins are going to be just like that. They're going to be a tube or a section that particles can move through to the other side of the membrane. Carrier proteins are going to literally pick up and move particles to the other side of the membrane.
Is that from the library?
No, that's from in my back room.
You know those? They have them at the library.
I have one from my back room.
Is that not from the library? Yeah. I see
Anyone need more time? Okay. So, just remember that diffusion, whether or not it's facilitated, does not require energy. So these particles, these proteins, do not need energy to work. They just work on their own. They passively move the molecules through the membrane. They are moving down their concentration gradient. They're moving from a high concentration to a low concentration. So the last thing we are going to talk about is something called osmosis. So osmosis is going to lead us into tomorrow when we talk about tonicity. Osmosis is going to be the movement of water. So osmosis, what's going to happen? Water is going to have to move from an area of higher concentration to an area of lower concentration. And how it's going to do this is it's going to have to do facilitated transport. It's going to need a molecule called an aquaporin, which is another transport protein. And it is, even though the picture is not on here, they are going to move from, again, high concentration to low concentration. So if we want to let water into our cells, we need to use proteins. If we are just using it for, if we had like a membrane or something, we could just let it pass through. But water, again, is going to be like all these other molecules that want to get from a high concentration to a low concentration. They want to get from a more dilute area to a less dilute area. Only 9-minute recording, that's not bad. Anyone need more time? Okay. Nope. So again, if we made this little loop, so this is a loop of pipe, and we have our selectively permeable membrane down here. If we put water in both sides, put a high concentration of, let's say, salt on one side and a low concentration of salt on the other, the water is going to move from the side with the less solute, so solute you remember back to our universal solvent, we had solvent and solute. Solute is going to be the thing that is dissolved in water. The water is going to move towards the area that has the higher concentration of salt. So in this case, the tube will fill up on this side because there is more salt on this side than there is on this side. So like I said, we will talk more about this tomorrow when we talk about tonicity. It's very amusing. We'll watch cells pop like little balloons. It is very amusing. A little morbid, but very amusing. I think I will start tomorrow with this video. That's on. So, with your partner, just like we did for the first section, please jot down the 3 main points of what we've talked about today. Okay, so Peyton, give me one.
Passive transport requires no energy.
Passive transport.
Requires no energy.
Yeah, thank you, Peyton.
Yeah, you're welcome.
What?
I don't know. We have some mockingbirds in here.
Jeez, no.
I'm hearing an echo. So yes, passive transport requires no energy. What's another takeaway? Have a go.
With Brownian? How do you say it?
Brownian.
Brownian.
Okay. Brownian.
Okay. Molecules are always in motion.
Okay.
We get retakes. Why would I do that? No.
Okay, so molecules are always in motion. What are they in motion for? Where are they going?
They're traveling through the membrane. Through the low
Okay.
concentration to high concentration.
They're going from high concentration to low concentration.
The post, the all post ones.
So all particles want to move from high to low concentration. And what was the third takeaway? Anything?
Channel and carrier proteins assist in facilitating diffusion.
Channel proteins open and close, and
Okay.
carrier proteins change shape.
Okay, so proteins. Okay. One other one you will want to remember. Like I said, we are going to be talking about tonicity tomorrow. One thing you will want to remember is what osmosis is. Osmosis? Yes.
Fusion of water.
So osmosis is water. Have a nice day, everyone.